Hi guys, welcome to a lesson of partial differential equations. So we are in the discussion of the topic that applications of Fourier transformations for partial differential equations, and we solve some problems. Now let's take one more example. For instance, if we have an equation u dt plus u x that is equals to negative x e to the power x squared, right? Or more generally, we can write it as negative x e to the power negative ax squared. Okay, and then we have the initial condition, or first of all, we should say that it's on the infinite domain, and the initial condition, that is ux0, is given by some function of x. Okay. Now, we know that we have to apply the transformation on the equation first. So we'll apply the Fourier transform on the equation. So u dt plus Fourier transform uxx equals Fourier transform of negative x exponential negative ax squared. Okay, so the transformation of this function we already discussed. It will be d squared u over dt squared, plus then the transformation of this function is negative omega squared u equals. Now for this function, how can we find the transform of this function? So we have a property of the Fourier transform that if we know the Fourier transform of a function f of x, for instance, then we can compute the Fourier transform of x times the function of x. So let's say x to the power n, because there can be x of any power, so can be x squared x or something like that. So it will be simply uh, equals to x to okay, it will be equals to iota power n times the derivative, and it's the n times derivative. N times derivative, it simply means that whatever power you have here times the function of omega. So this function of omega is nothing but it's the Fourier transform of this function, right? So by using this property, we can first of all, we can take this negative sign outside, and then uh, x times, so we can write Fourier transform of x times, if we know the Fourier transformation of this function, that is exponential. So let's write here this way. So now we have the Fourier transformation of exponential to the power negative ax squared. We already computed this transformation. Fourier transform of e to the power negative ax squared is simply negative infinity to infinity e to the power negative ax squared dot e to the power negative iota omega x dx. So we will see how can we compute this in the lesson of Fourier transformation. Right now we are only using the result, so it is square root pi over a times exponential negative omega squared over 4a. Okay, so now we can use this result and that property of Fourier transformation. So the property says that Fourier transformation of x to the power n times a function of x is nothing but iota power n dn over dx n times the function of omega. Sorry, it's not dxn, it's d omega n, right? Because we have the function of omega inside. So it's d omega n. Okay. So now f of w, what we get is simply this thing, pi over a times exponential negative omega squared over 4a. Now we have to take the derivative of this function because we have x times the function of x simply, right? So it's x times exponential to the power negative ax squared. So we can simply differentiate 1. So it will be iota to the power 1 because the power of x is 1 here, and d over d omega. So simply we have to differentiate this once and we will get the desired result, right? So we need to differentiate this function. So it will be iota times, okay, so the square root pi over a e to the power negative omega squared over 4a times negative 2 omega a. This is times the derivative of the power, so it will be negative 2 omega times divided by 4a. Okay, so now we differentiated this function, and so we can simplify, so it will be negative iota omega square root of pi times e to the power negative omega squared over 4a divided by 2a square root of a, right? So now this is the Fourier transformation of this function, that is x e to the power negative ax squared. And here we already have the negative sign. Here we already have the negative sign outside, so it will become positive. So now the equation we have is d squared u over d squared negative omega squared u equals iota omega, and we should write here square root of pi over a divided by 2a e to the power negative omega squared over 4a. All right. So now this is a second order differential equation, and it's non-homogeneous with constant coefficients. So we can simply make the auxiliary equation to find the homogeneous solution, and then we will try out the particular solution. So this implies R equals plus minus omega, which gives the result that u of omega t is now equals to a e to the power omega t plus b e to the power negative omega t. And then we have this is the homogeneous part, so we can write UH, and for the particular solution simply we can see that it's pretty simpler. So this omega squared will be shifted to the right side, and we can simply find this by using the method of undetermined coefficients. So I'm writing it directly, so it will be negative square root of pi over a iota over 2 omega a e to the power negative omega squared over 4a. So this is our UP. So now U will be simply equals to the linear combination, or we say sum of these two solutions, that is UP and UH. So we can write it as negative square root of pi over a iota e to the power negative omega squared over 4a divided by 2 omega a. So this is the solution in terms of omega t. But we know that we need the solution in terms of uh, xt. So first of all, we need to apply the initial conditions. So for the transformation of the initial condition that is given is ux comma 0 equals f of x. So the Fourier transformation of this will be nothing but it will be some function of omega. We can write in this way, okay? So now we apply the condition here. So it's u of x, no more x, now it's omega. So it's u of omega comma 0 equals a plus b negative square root of pi over a iota a to the power negative omega squared over 2a over 2 omega a equals f of omega. Now this is we can say equation 1, and then the other condition that we are going to use here will be, as we are talking about infinite domain, and we can see that if t tends to infinity, the solution should be the solution vanishes, right? So it's another condition that is also given in the question, that as t tends to infinity, the solution vanishes, right? So it's condition, this condition is given in the question. So I forgot to write above, but if this is given, t tends to infinity, the solution vanishes. All right. So the solution vanishes, fine. Then what will happen means that u is simply going to be 0. So we can say that u of omega comma t as t goes to infinity, it's a e to the power infinity plus b e to the power negative infinity minus square root by a iota e to the power negative omega squared over 2a over 2 omega a. This is equals to 0. So we can shift this to the right side. Now this will be 0, and this will be a e to the power infinity equals a square root pi over a iota e to the power negative omega squared over 2a over 2 omega a. Now if I shift this infinity to the right side on in the denominator, then we are going to get a equals 0, right? Because this infinity in the denominator will make the whole term 0. So a equals 0 means now the solution I have is only b e to the power negative omega t minus square root pi over a iota e to the power negative omega squared over 4a divided by 2 omega a. And similarly, now I can use this a equals 0 here. So a is 0. So b is equals to simply, so u of omega comma 0 implies that b equals f of omega plus square root of pi over a iota omega negative omega squared over 4a over 2 omega a. So this is the value of b. Now the complete solution in terms of omega t will be b times this function, b times, okay, so it's f omega plus square root of pi over a iota e to the power negative omega squared over 4a over 2 omega a times e to the power negative omega t minus square root pi over a iota e to the power negative omega squared over 4a over 2 omega a. All right, so now to get the solution, we need to apply the inverse transformation So by inverse transformation, on the left side, we'll get ux comma t, and on the right side, we just simply need to uh, integrate the function from negative infinity to infinity. Also 1 over 2 pi in the denominator, this thing, and then this whole function. So this whole function is function of omega. So we can say that this is g of omega, for instance, times e to the power iota omega x dx. So in this way we can, sorry, not dx, it's d omega. So this way we can find the solution for this particular equation that is given here. So the solution to this equation is given in the form of integral, and I hope you guys will understand this problem as you solve it step by step and defining each step. So that's all for the time being, and we'll be back in the next lesson with some more problems. Thank you.